This is another video lecture from Math 1053 at UTSA. This week we're doing Module 4, Systems of Linear Equations in Two Variables, as well as linear inequalities. I think that's probably, yeah, linear inequalities and systems as well. So there's kind of a lot in this section in the sense that there's two different topics, but they're highly related. Just covering um, just systems of linear equations in two variables, that would not really be a full week worth of content. So we're doing inequalities as well, and we'll expand upon that later. I think Module 5 actually is on what's called linear programming. So we're going to start with making sure we understand what it means for an ordered pair to be a solution to a system of equations. So let's sidetrack just a little bit and talk about a solution to just an equation in general. So like if I had something like 2x plus 1, plus 1 equals like 19 or something like that, right? You could look at that, and even if you didn't understand the algebra involved, if you understood the arithmetic involved, you understood what is meant that, oh, you got to find a number that when you plug it in, the left will be 19, you can work out, oh, that needs to be 9. So 9 is the solution to the equation, right? Of course, when we're doing algebra, we would have a list of steps, like, oh, subtract 1 on both sides, right? So 2x equals 18. And then divide 2 on both sides, so x equals 9. So if you understand the algebra, you can go through the steps to get the number without guessing. If you don't understand the algebra, you can try guessing, and maybe that will work, depends on the equation. So let's pretend like we've got this pair of equations, and we've been given a guess, and we just want to determine if it's a good guess or not. You probably wouldn't want to solve a system of equations like this by guessing, but you could try it that way. So if we were doing that, how will we check that this is right? If we just straight up guess -6, 1, how do we check that? So the first number, this is an x coordinate, and the second number, this is a y coordinate. Maybe that was obvious already, but this is like an ordered pair, as in when you're graphing a function, you're graphing a series of points of ordered pairs. So basically what we'll do is we'll take the first equation and plug in -6 for x. So -3 times -6 minus 5 times 1, and we're going to see if we get 13 this way. And if we do, well, then that pair is a solution to that first equation. So -3 times -6 is 18, right? Minus 5, well, that is 13. So this ordered pair, basically what this is saying is this ordered pair is a point on the graph of that line, okay? That those numbers, when plugged in, match the equation. Therefore, the graph of the equation has that ordered pair as a point on the graph. And then we can check the other equation. So we'll plug -6 in for x on this one, and then plug in 1 for y. So -6, that's +6, plus 4 times 1 is 4, and we get 10. And that checks out. So that means that, yeah, that order pair is a solution to that equation as well. So that means that it's a solution to the pair of equations, the system of equations. In other words, well, up front, it might not be obvious that two straight lines only cross at one point, but maybe it is obvious. I mean, we're not looking at a drawing, so maybe it's not obvious on the face of it. But when you have more than one equation, these equations when they have two variables, they each have a graph, and the graph of each of these equations is a straight line, and straight lines can only cross at one point, or they can be parallel, or they can, well, there's some other options, but they can't cross twice. You can't have two straight lines crossing 3 times. It doesn't work that way, right? So when you are finding the ordered pair that solves the pair of equations, you're finding the point where they intersect. If you have a pair of equations that are not linear equations, as in the graphs aren't lines, like if they're parabolas or whatever else it could be, there's different types of functions, they're not all linear functions, then there could be lots of intersection points. And when you are looking for a pair, the solution to the system of equations, that gets harder when they're not linear. When they're linear, it's fairly systematic, kind of like we have this system over here for solving this linear equation, right? You isolate x. We have a similar technique for handling pairs of linear equations in two variables. You can also do this, by the way, with 3 equations or 4 equations or 5 equations. It just gets more complicated, though. And in this class, we're not doing that. The next one's pretty much the same thing. I don't remember off the top of my head if this one does not solve the pair of equations. Although if I had prepared this document, which I didn't originally prepare it, then I would have made sure some of them don't work. But I'm guessing this one does. So if we plug in -1, 1 into this equation, the left-hand side at least, well, -2 times -1 is 2, plus 5 is 7. So that checks out. So that order pair does solve the first equation. Plugging in the next one, so 2 times -1 plus 9 times 1. So we get -2 plus 9, which is 7. Okay, so this order pair also solves this pair of equations. So in other words, the point where the graphs of these two straight lines intersect, that intersection point, that's that ordered pair, -1, 1. Okay. So if I want to do like a rough picture of what they looked like, based on that, this is not in the homework, but if I wanted to do that, here's what that would indicate. If I plot the point -1, 1, like let's say it's right here, right? That means that these two lines over here, well, they're going to look like maybe like that and well, that. Let's pretend I drew that better, right? They're going to cross at that intersection point. So they make like some sort of X shape. They cross. Anyway, that's not accurate. I was just doing it really roughly to illustrate what I meant about the intersection point. Anyway, that's basically it for if you have a potential solution to a pair of equations, you just plug it into each equation to check that it really does fit both equations. And if it does, well, then that's I should say it's a solution to the system of equations, because sometimes there's more than one. In this case, there aren't. So now what if we don't have a guess? And maybe you could look at this. Maybe you could guess if you just thought about it. If the correct answer doesn't have fractions in it, right? If the correct answer has fractions, well, then good luck guessing, right? But if the correct answer is whole numbers, then maybe you could do that, right? But there's actually two primary methods. One is called substitution, and the other is called elimination. Okay, and they both work. They kind of do the same thing, and it's I guess generally speaking, if you only knew one of them and not the other, that would be fine, because any system of equations can be solved with either method. And especially if we're only doing two equations at a time, then they're pretty much kind of the same. So if one of them makes a lot more sense to you than the other, then just do that. I think that so obviously in web work, even if the problem tells you, oh, you need to use substitution for a homework problem, well, how does it know if you did that or not, right? The answer is the answer, right? It's not, web work is not checking your steps, it's checking your answer. So you don't have to really worry about that in web work. On exams, I don't already know off the top of my head the directions for the exams, what they're going to be. But I'm imagining that the exam problems will not tell you, oh, you have to use this method or the other method. I don't really care about which method you learn, as long as you kind of understand what to do. So if one of them is way easier for you than the other, then just do that one all the time. In some sense, ideally, you would understand both, but if one's easy and the other's super difficult, maybe just go with the one that you understand better. Anyway, so let's look at these two methods. I'll show both. For this first example, I'll do both. And for the other examples, I'll do one or the other depending on the numbers involved, whatever seems easiest at the time. So let's first do substitution. The way substitution works is that you'll pick one of the equations. I'm going to pick this one, okay? And then you're going to isolate either x or y and get either x or y by itself. Okay. Now, I should point out at the very beginning here that the steps I'm going to use are actually not the most efficient, because substitution kind of isn't the most efficient for this particular pair of equations, but we'll just go with that. Once it's kind of like PEMDAS, where PEMDAS always works. It's like a recipe. If you just follow it, it will work. But you don't always have to stick to the recipe, right? If you're cooking something, you got a recipe online somewhere. It's not like if you deviate from that recipe by 1%, then it's just totally going to not work. I mean, baking is one thing, but like to say it's like, I don't know, you're making baklava, right? Which is baked. You got to be really precise. If you're making some sort of soup, well, It's not baked. Don't need to worry about precision as much, right? You just kind of throw stuff in there. So the point is, substitution, the technique, I'm going to show just in simple terms what it is, but you don't always have to follow it step by step, literally the way I say to do it. Anyway, let's not waste any more time. So like I said, I'm going to get x by itself. So I'm going to subtract 3y on both sides of that equation. So I'll write the equation out. And at some point, we're probably going to run out of room. I'll need to like scroll down or to the right or whatever. So I'm going to subtract 3y on both sides. In the interest of saving a little bit of space, I'm not always going to write, like I didn't write minus 3y on both sides and then like cross pieces out and rewrite it again. I'm just trying to save vertical space a little bit. So we get x by itself. Then what we're going to do is we're going to substitute this x in for that one. So we're going to have 2 times 5 minus 3y. That's the x that we substituted, right? Because x equals 5 minus 3y. And then plus 3y equals 4. So what we did, basically, is we combined the two equations into one equation that no longer has x in it. It only has y as a variable now. So I can solve this equation a lot like we did in this the previous one, the one up here, where we just had an equation with just x, no y in it. Now we have an equation with no x, sorry, just y in it, so I can get y by itself. So basically, you take the two equations and through some mechanism, you plug one into the other, or you plug them together somehow, and substitution is one way to do that. So to get the rest of the problem, or get the answer, I should say, so we'll distribute that 2, so 10 minus 6y plus 3y equals 4. I'll go ahead and combine like terms. We'll have 10 minus 3y equals 4. I'll subtract 10 on both sides. So negative 3y equals negative 6. And then divide by negative 3 on both sides. So y equals 2. So now we have a number for y. We have a y coordinate, okay? Now, to proceed, the next thing is we need an x coordinate. And really, you can take this y value that you got, or that we got, and go plug it into either of the original equations, or into this one, which is the same one, I just rewrote it, or this one. So any of the other equations that still has both x and y, any of them, doesn't matter which one you pick, you can plug that 2 in for y and solve for x, and you'll get a number that way. You'll get an x number. The one that we're going to want to use is this one. Oops, not that one. This one, because x is already isolated. So if I plug in 2, I'll have 5 minus 6 is negative 1. I don't have to do any algebra. It's just arithmetic. Whereas if I were to plug in to say this one, right, plug in 2 for y, I'd then have to do some algebra to get x by itself again. It's just a waste of effort. I really don't need to do that. And especially like on a timed exam, then I don't want to do it that way, right? So I'm going to plug in y equals 2. Oh, again, sorry, not that one. This one. So x equals 5 minus 3 times 2, so 5 minus 6. Oh, let's write that more neatly. 5 minus 6, so negative 1. Okay, so the ordered pair is negative 1, comma 2. And then if we want, we don't need to necessarily, but if we want, we can take this ordered pair and go check it in both of these equations to double check that it works. It should, right? But maybe we have a mistake. So if you want to check for a mistake, you can do that. I'm not going to bother doing that here. So that's substitution, okay? You pick one of the equations, isolate one of the variables, plug into the other equation, and then solve for that other variable to get a number, and then go from there. So again, we could even say for substitution, let's actually do this. Let's list the steps out. That might be helpful. Probably, I'm guessing though, if you've done the textbook notes, that's in there somewhere. But it doesn't hurt to just list them out real quick. So 1, pick an equation. Okay, abbreviate equation here. Isolate a variable. Doesn't really matter which one. Okay. Substitute in other equation. Isolate the variable that remains. I guess remaining variable is fine. Okay, and you get a number that way, right? Either x or y. Then plug value into one of the earlier equations. Again, it doesn't really matter which one you plug into as long as you go back to one of the equations that has both x and y. It doesn't really matter. You'll get the right answer, but which one you pick might save you a little bit of time. So one of the earlier equations and solve. So the textbook might have slightly different steps, but that's pretty much what it is. It might have consolidated two steps into one step, like steps 1 and 2 in the textbook might be given as the first step, like as the first individual step, rather than have it being two separate steps. That's the way I think about it. So let's rework this same problem, and of course get the same answer using elimination, just to show what that is. Okay, so let's do this. Yeah, we got some room over here. Okay, so now we're going to do elimination. Okay, now the way elimination works is that you want to combine the two equations by adding or subtracting. Usually we'll do adding in order to eliminate one of the variables. What do I mean by that? Well, kind of like if you have like a equals 2 and b equals 3. This might seem weird, but you can add the two equations together, add the two left-hand sides, add the two right-hand sides, and that produces a new equation that is consistent with the two original equations, like a plus b equals 5, right? If a is 2 and b is 3, then a plus b is 5. And you can do that with just equations in general. So if I take these two equations and I were to subtract them, okay, well, x minus 2x is negative x, sure. 3y minus 3y, that cancels, that's 0. And then 5 minus 4, that's 1. So we get negative x plus 0 equals 1. So negative x equals 1. And then I can divide by negative 1 on both sides and get x equals negative 1. So that's elimination. And the elimination step only gives you x or y numerically. It only gets you a number for one of them. You have to go back and get the other one separately. And you can either do elimination again by eliminating the other variable. So I'm actually going to do it that way. Usually what you would do is you would use elimination, get this number, right? X equals negative 1. And then usually you would then go plug that negative 1 into one of the original equations and then solve for y and get a number that way via substitution. But you don't have to. So let's actually not do that in this case because I want to illustrate something. I've run out of horizontal space here. So let's do this. I'll move this over just a little bit. I'm going to copy this. What I'm going to do is, since we've already eliminated y in order to get an x value, now we need to eliminate x in order to get a y value. And there's a couple of ways to do this. What I'm going to do, this might seem a little weird, is you know how you can multiply both sides of an equation, like up here? We divided by 2 on both sides, and that's something you're allowed to do on an equation, right? You can multiply, divide, add, subtract on both sides, right? What I'm going to do is, on this equation, I'm going to multiply by negative 2 on top, I'm sorry, not on top, bottom, but on left and right on both sides. So this group then becomes negative 2x minus 6y equals negative 10. And the other equation doesn't change. And now if I add the two together, then the x's will cancel completely. So I'll get negative 2x plus negative 2x is 0. Negative 6y plus 3y is negative 3y. And then negative 10 plus 4 is negative 6. Okay, I've eliminated x. I can drop that 0. We don't need that. And then divide by negative 3 on both sides. So y equals 2. So we get the ordered pair negative 1 comma 2, which is, of course, the same answer we had just gotten. And I never had to plug anything into anything. I never did any substitution at all. I just didn't need to. Now, the point I was going to make a moment ago is that, well, I mean, I guess I kind of made it already, is that you can mix these two approaches together. You can find X via substitution and then Y via elimination, or X via elimination and then Y via substitution, just whatever you want to do. Both of these techniques get the answer. And sometimes it's most efficient, and you only learn that by doing multiple problems and figuring out the pattern. It's sometimes most efficient to use both techniques, first one, then the other. Sometimes not. Sometimes just use elimination only. Sometimes just use substitution only, but they're mixable. You don't have to use only one or the other. So the process for elimination, which we didn't say what that is. So the steps for elimination are the following. Hold on, struggling with the interface here. I guess I did not need to copy literally that one, but why not? So here are the steps. Basically, you need to identify. Oops. I should say identify. I should say just pick. Pick a variable to eliminate. And sometimes it's super obvious. Like with this one, the 3 y's, these were already both 3 y's. So if I just subtract the two equations, then the y's go away. So sometimes it's very clear what elimination should happen first. So pick a variable. So pick a variable. Then you need to multiply each equation by a number that will result in the coefficients of that chosen variable being the same, as in like 3y and 3y, or opposite, as in negative 2x and positive 2x. Okay, so that's kind of a mouthful, but you're going to multiply each equation. How about this? How about this? Identify. Now we're using identify. The least common multiple, that's what you would end up using, the least common multiple of the coefficients on that variable, because there are two equations. Each equation will have one coefficient for that variable. So identify the least common multiple of the coefficients. And this is all assuming that x and y are both on the left side of the equal sign. If they're on opposite sides, this changes things, but I'm just assume that. Identify the least common multiple of the coefficients on the chosen variable. Okay. Multiply each equation by a value that will cause the resulting coefficients to match. Yeah, putting it in like a checklist is a little bit harder with substitution. Multiply each equation by a value that will cause the resulting coefficients to match. So what I mean by that is like with this one, I had x and 2x. So I multiplied the top equation by -2. So I'd have -2x. So that when I add, then the x's will cancel. And if the coefficients are the same, as in like they're both +3, well, then you would subtract the equations. If they're the same in the sense that, well, they're both 2, but one's +2, one's -2, but they're matching, right? Well, then you add the equations. So you can either add or subtract. It doesn't really matter which one you do, whichever is appropriate to the numbers that you have. And you kind of only learn that by doing enough of these, you kind of get the pattern. Okay, so multiply each equation by a value that will cause the resulting coefficients to match. Add or subtract the two equations. To eliminate. the chosen variable. Sorry, trying to write quickly, which results in poor handwriting. Variable, and then solve for the other one. Okay, so that's basically it. 5 steps in either way, either case. Just for one of them, the 5 steps, it's real easy to say what the steps are. For the other one, it's hard to say what they are. And part of that is with substitution, you're pick a variable, or sorry, pick an equation, pick a variable, isolate that variable, and isolate that variable. That has a lot sort of built into it. Well, you're going to have to subtract on both sides, or divide on both sides, or do stuff. Whereas here, we're having to say more clearly what it is that you're doing because it's not just isolate. You all know what isolate a variable means, whereas this part I have to kind of explain in detail what it means to pick these numbers. But really, it's the same. You might even notice if you go back and look here, you might even notice when we had like I don't know this one, negative 3y equals negative 6, right? It's right here. It's the same thing, right? Um, and like so the arithmetic that's happening here, the way that the numbers are combining and recombining to make the resulting answers, it's the same thing that's happening over here, just in a different order. And so yeah, they're basically the same thing is happening. So that's in a nutshell substitution and elimination. Okay. So let's go do a few more of these, and I might have to like kind of find space because I kind of ran out of. You know what? Let's do this. I think it'll just be fine. I'm not going to worry about it. The one thing I will do is I'm going to move this kind of over here out of the way. Over here. Okay. So next example. So this one has fractions in it, which does make things a little bit harder. What I'm going to do is I'm going to start by multiplying each equation on both sides, both left and right, by the least common multiple of the denominators that are present in that equation, so that I can get rid of fractions and not have to deal with them. Okay. So in the first equation, I've got two denominators, right? 4 and 2. The least common multiple of 4 and 2 is 4. So if I multiply this equation on both sides by 4, then on the left, the fractions will go away. And on the right, I'll have 44. So the numbers will change on both sides, but then I won't have fractions anymore. Okay, so we'll multiply by 4 on both sides. The second equation, we've got an 8 and a 3 in the denominators. So I'm going to multiply by 24. That's the common multiple of 8 and 3. That will eliminate those fractions. So it's a little crowded here. Yeah, let's do this. I'm going to change the stylus. Hopefully this is not hard to read. So times 4 on both sides here. And then times 24 on both sides here. Okay. So, yeah, let's put it down here. So when we multiply here, 4 times negative 1/4 will be negative 1, right? So negative x. 4 times plus 3 halves, right? You could think of that as being 12 over 2, which is 6. I prefer to think about it. It seems easier to me to think about the 4 and the 2 canceling and reducing to having 4 on top there, and then the 2 just cancels, becomes a 1, and 2 times 3 is, of course, 6. Either way works. I find that reducing fractions as I go, it just seems easier because then the numbers don't get large. So anyway, we get negative x plus 6y equals 44. And then the next one, 24 times negative 1/8 will be negative 3. And then 24 times 1/3 will be 8. So I'll have negative 3x plus 8y equals 72. Okay. Now from there, I can do substitution. I can do elimination. Doesn't really matter. Just get to pick one. I'm going to go with, I guess I'm going to go with substitution for this one. And the reason for that is that this x is kind of, the isolation part is partially done for me. I'm not going to, I don't know. It just seems like it might be easier than substitute, or sorry, than elimination, just because of this. I'm gonna isolate x in that first equation. So I'll bring that up here. So negative x equals negative 6y plus 44, right? Because subtracted 6y on both sides. And then I'll take that equation and divide by negative 1 on both sides. So x equals 6y minus 44, right? And then that I will then substitute into this equation, but I'll write it here on the next line. But I'm substituting in for this x right here will become 6y minus 44. So negative 3 times 6y minus 44 plus 8y equals 72. Okay, so distributing the negative 3, we get negative 18y plus 132. I think that's right. I'm sure if it's wrong, well, it'll get fixed eventually. And then I can combine like terms on the left, so I'll have negative 10y plus 132 equals 72. Then we can subtract 132 on both sides, so we get negative 10y equals negative 60. So I'm pretty confident this is correct, because this is going to come out to be a nice clean number, a whole number really. So then divide negative 10 on both sides, y equals 6. Okay. And then I can take this 6, the y equals 6, and go plug that back into here and get x equals 6 times 6 minus 44. So that's 36 minus 44, so I get negative 8. Okay, so the ordered pair is negative 8, comma 6. Okay? And what you might want to do, just for your own benefit, just for extra practice, is rework this problem using elimination and just see how it goes, and you should get the same answer, just for extra practice. Okay, so let's do the next one, and let's use elimination for this one. Now, with number 4, I cleared the denominators first because I feel like that makes it a little bit easier. I'm going to do that here too, except that we don't have denominators really, right? We have decimals, but of course decimals kind of are fractions, like 0.6. Oh, hold on. My stylus stopped working. Okay, there we go. So 0.6, this is 6 over 10, right? This is a fraction. It's just, written without fraction notation, but it's essentially a fraction. Writing a decimal instead of a fraction is largely a format difference, not really like a mathematical difference, right? So what I'm going to do is I'm going to multiply by 10 on both sides of this first equation. And I'm definitely not going to really have room there, but we'll just kind of put it there and it'll be fine. So this becomes negative 2x plus 4y equals 6. And then the bottom equation, nothing happens to that, at least not yet. Yeah, I probably should have modified that one as well, but that's okay. That's fine. Okay, so we got negative 2x plus 4y equals 6, and then x minus 2y, not negative 6, negative 3. Glad I read that again. Okay, so I want to do elimination, so I need to modify the bottom equation so that it either I'll have negative 4y here, where the negative 2 is, that way when I add, the y's will cancel, or I need to have a positive 2 here, so that when I add the two equations, the x's will cancel. So I need to, I guess in either case, and maybe see where this is going, I kind of need to multiply both sides by 2. Okay, so the next version of this, which I guess we'll go over here. So we'll have negative 2. Oh, and by the way, what I probably should be writing, but I wasn't doing, is putting that little bracket in front of the pair of equations every time. That indicates, hey, this is a group. They go together. So I probably should start with that. So negative 2x plus 4y equals 6. And then on bottom, 2x minus 4y equals negative 6. So that when I add these together, well, the x's cancel, but also the y's cancel, and also the 6's cancel. So you might wonder, well, what does that mean? If we try this elimination method and we get 0 plus 0 equals 0, which is true. Well, what that means is that these two equations really represent the same line. They're slightly different versions of the same line. So um, if we had, instead of multiplying by +2, if we had multiplied by -2, right, then this would be -2 here, this would be +4 here, this would be +6 here, right? If we multiply by -2 on both sides, and it would be clear, like, oh, these are the same equation. So if you have two equations that don't look the same, and while you're, trying to solve the pair of equations, you might notice, oh, wait a minute, these are the same. Maybe you'll notice, but maybe not. It depends. But if you get to the end and you get 0 equals 0, then that means that they're the same equation. So there are infinitely many solutions. So basically, uh, well, there's not like a question here. Like, well, what is the statement? It says solve each system by any method. Yeah, there's not like really sometimes there's a specific way of saying what your result is. I think that in web work, some of them will have like a little drop down menu where you select, oh, there's one solution, or there's many solutions, or there's no solution. The individual problem will it'll tell you how to interpret that. But basically with this one is that we basically have the same line described by both equations. So that means that there's infinitely many solutions. So this is what's called a dependent system. And what that means is that really the second equation was redundant. It doesn't add anything to the pair of equations. The second equation being equivalent to the first equation means that you just throw it away. It doesn't do anything. So there's lots of solutions, and they're the ordered pairs that solve either one of these equations, and there are lots of them because they're both. I mean, I keep saying that they're both, but they're really the same line. The two equations, which are apparently different, but actually the same line, right? You don't need both of them. Now, the one I've highlighted is the nice cleaner numbers. So that's probably the one you would want to think about. Oh, this is the equation for the line. Even though, of course, there's many of them, right? So this is called a dependent system because one equation depends on the other in the sense that, well, it's kind of the terminology doesn't make a whole lot of sense when you have two equations. The way it works is if you have 3 or 4 or 5 equations, when this happens, say you have 4 equations, right? And one of them is redundant. It doesn't add to the system in effect what the solution is or solutions are. We would say, oh, that this last equation is just dependent upon the first ones to determine the solution. It doesn't add to it. So when you have multiple equations, calling the system dependent because one of the equations is redundant kind of makes more just English sense. Whereas when you have two equations, saying that one's dependent on the other just kind of doesn't really work. Well, if they're the same equation, how does one depend on the other? Like, what does that mean? In a different context, it makes a little bit more sense. Anyway, we don't need to worry too much about that because that's not the context we're dealing with right now. I'll try to avoid going on side note rambles, but that's going to happen sometimes. Anyway, so this brings up an interesting question, I think. So if this is called dependent, what is this one called? So a pair of equations where you get a solution, you get a single solution. This is what's called a consistent independent system. Okay, consistent, independent. I guess you could think about it as, yeah, this might be a good analogy to, if maybe the terminology already makes sense, but perhaps not. You could say that a system is independent when you get a solution because the two equations are doing different things. They're independent of each other. The two equations are just doing their own thing, and they intersect, and there's an intersection point. Okay, it's consistent because there's a solution, but the system is independent because the two equations are doing different things. This one's called dependent because these two equations are just the same equation. It's like, if you if you have like a kid and your kid goes everywhere you go, right? If you go to Target, your kid has to go with you. You can't just leave them at home. Like if they're like 2 or something, you just leave them, right? They're dependent on you. They have to go with you. They go where you go. So in a dependent system, one of the equations is not adding to the solution. It's just kind of there. So in a dependent relationship, it's kind of similar. So whereas versus independent, this is called independent because the two equations are doing something different. So there's an analogy that might make the terminology make sense if you needed that. Maybe you didn't. but if you did. Okay, next example. So this one's kind of similar to the others in that, hey, it's just a pair of equations. This one, I don't know. I'm guessing, because there's a third type. I'm guessing that we're not going to get a solution here. That's entirely a guess. I didn't work this out ahead of time. I mean, I used this example before in prior semesters, but I don't remember it from months ago. So what I'm going to do is I'm going to start like we did with number, I guess it was number 2. Oh, 4. Yeah, number 4, where I was clearing denominators first. So this first equation, I'm going to multiply the equation on both sides by 9 because I want to get rid of the fractions. And on the bottom equation, I need to multiply by 30, okay? Because 2, 5, and 3 don't share any factors. They're all prime numbers, right? And so their common multiple will just be the product of 30. Okay, so we'll put that down here. So 9 times 1/3, that'll make 3, so 3x. 9 times 1/9 is 1, so 1y. And of course, 2 times 9 is 2. So 3x plus y equals 2. Okay, and then 30 times -1/2 would be -15, so -15x. 30 times 4/5. Again, I'm going to think about the 30 and the 5 is reducing to be 6 and 1. So 6 times 4 is 24, so 24y. Okay, and then 30 times -1/3 is -10, of course. Okay, so we get -15x plus 24y equals -10. Okay, yeah, I was kind of expecting these to be what's called an inconsistent system, which we'll talk about in a second, but apparently not. Okay, unless I've made a mistake, these don't appear to be that. So for this one, I guess I'll use elimination again. Yeah, we'll do elimination again because that one didn't really go anywhere. So we'll do elimination again. Okay, so if I want to eliminate, I guess I want to eliminate the x because I see that if I multiply this by 5, then I'll have 15 here. So I want to multiply this top equation on both sides by 5. So that will go over here. So 15x plus 5y equals 10. And then minus 15x plus 24y equals -10. Okay. So when I add those together, I get 0x plus 29y equals 0. So 29y equals 0. So y equals 0. Okay. Now to get x, I don't have to use elimination. Like I said earlier, you can mix elimination with substitution. So let's actually do that. I'm going to take this 0, and I'm actually going to plug it into, for y, into this equation. Because remember, I said that when you do substitution, go back to any of the equations that have both x and y in it and plug in 0 for y, and you can solve for x. It doesn't matter which one you pick. Just pick one of them. They'll all work, but the one I highlighted in green, I think that one will be slightly easier. So then, well, I guess I should do that over here. 3x plus 0, y is 0, equals 2. So 3x equals 2, so x equals 2/3. So sometimes you're going to get a fractional answer. Your answers won't always be whole numbers. Like, maybe that's obvious. These were all chosen carefully. Like this one. This is chosen to make sure the answers were whole numbers. And this one was probably chosen to make sure one of the answers was a fraction, most likely. I was kind of expecting to have what's called an inconsistent system. We didn't have one of those. So what would that look like? Well, maybe we'll get one later, but let me just sort of make one up on the spot. What would inconsistent look like? Okay. So, so when you have a consistent system, you get something like this, where you get, if you graph the equations, there's an intersection point. That's a consistent independent. In fact, I'll put the drawing right here. You get something like that, okay? Because the two lines cross. When you get something like that's dependent, what you get is something like this. You have a line, but then the other line, it's the same line. Like I wobbled there at the end, but it's the same line. So there's infinitely many solutions. All of these ordered pairs, these are all solutions. There's a bunch of them. An inconsistent system looks like this. I'll show you the graph, and then I'll give you an example as well. Like what would the algebra look like? So in an inconsistent system, you're gonna have two lines, one like this, and then one like this, and they're parallel. Okay, so in an inconsistent system, the lines are parallel. When you have two equations with two variables, if you, like I had alluded to earlier, you can do this same algebra with 3 equations, 4 equations, 5 equations. When you do that, you'll have either 3, 4, or 5 variables typically. So when you are working with more variables, in other words, in the graph, more dimensions, there's many different ways to have an inconsistent system. But when you have two equations in 2 variables, x and y typically, then the only way to have a consistent system is when the lines are parallel. That's the only way that will happen. So a pair of equations would look like this. You might have something like 2x minus y equals 3, and 2x minus y equals 5. Something like that. And notice that the coefficients for x and y are the same, but the number on the other side is different. So any pair that solves this equation, where you plug in and you get 3, so like 2 comma 1 would be a solution to that, right? Right? If you plug in 2 and 1 on the left, you get 3, right? 2 times 2 is 4, minus 1 is 3. But then that does not solve that one, right? Because you plug in 2 and 1, you don't get 5, you get 3. So any solution to one of the equations cannot be a solution to the other one, because these numbers are different, okay? And you can have two that they don't look like they're inconsistent, but they actually are, kind of like how this one up here, hold on, struggling with the interface here. This one here at the beginning, maybe it didn't look like these, maybe it didn't look like these two equations are actually the same line. Like it wasn't obvious because the numbers look different, right? So you can have something like, let me see if I can make one up real quick. Well, this is going to be fun. So let's do this. Okay. Something like that. That is an inconsistent system. Okay, if you try to solve that, it won't work. Now, what happens when you try to solve these? Well, if I try to solve this via elimination or substitution, let's talk about elimination for a second. If I did that, go, oh, I need to multiply this equation by 3 on top and bottom, right? So that the pair of equations becomes 3x minus 6y equals 7, and then negative 3x plus 6y equals 3. And when I add the two equations together, I get 0 plus 0 equals 10, which is a false statement, right? It's a false statement. It's just not true. So, when you're trying to solve a pair of equations, you might notice pretty early, oh, these are parallel. Maybe you would notice that, okay? But maybe not. And the way you would notice is when you're trying to solve it and you get this false statement, 0 plus 0 equals 10, that's just false, it doesn't work. That tells you, oh, okay, that means that there's no solution. Okay, and when you do substitution, a similar thing will happen. You'll get an equation like 0 equals 1, or something like that. You'll get something that's just a false statement. Okay, so that's how those go. All right, what's next? So use systems of equations to answer the following. Okay, So the first one says, number 7 says, a fast food restaurant has a cost of production, C of x equals 5x plus 120, and a revenue function, R of x equals 11x. When does the company start to turn a profit? Okay, well, basically, this cost function, this is a straight line. When you graph it, you get a straight line. And this revenue function is also a straight line. If you graph them, you get something like the following. And it's certainly not going to be super accurate, but if you graph them, it looks something like the following. The revenue function is going to look like maybe like that, and the cost function is going to look maybe like that. And then they have a point where they intersect. This is the break-even point, because this x value, which I probably should left myself some space under the graph, but this x value here, that is the production level where costs and revenues will be equal. That's called the break-even point. Okay, so what we want to do is find the break-even point, and then it says when does the company start to turn a profit? Start to turn a profit. Well, if you're breaking even, your profit's 0. You'd have to advance. You have to make some more. Oh, typo. There should be a space there. You need to move forward in the x coordinate. You need to increase x by a little bit to start to turn a profit. So some of the, at least one of the homework problems is like that, where that your answer needs to be rounded up to the next whole number. Even if like you get x equals 5, your answer is 6, because if you get exactly 5 for the break even, well, you're not making a profit at 5. And we want to know, well, when do you start to make a profit? So you round up to the next whole number, even if it takes you from like 5 to a 6. So how do we do that? Well, basically, I want to say, oh, well, the revenue and the cost are going to be equal, right? So I can just say that, like, oh, well, y, the dollar amount for my cost, well, that's 5x plus 120. And then y, the revenue amount, is 11x. And I'm saying that C and R are both just y. They're just some y value because it's just some dollar amount. And we're looking for the break-even point, so I can just declare them to be equal and go, well, they're both equal to y, whatever that is. I don't know what it is yet, but I'll just say that's it. And then I can use substitution. I can say, well, I'm going to, since y equals 11x, wrong tool there. Since y equals 11x, I'm going to plug that in right there. And take this system of equations, pair of equations, and go, well, that means I have 11x equals 5x plus 120. And then I can solve that however I want. I guess I'll subtract 5x on both sides. 6x equals 120. Divide by 6 on both sides, so x equals 20. And then I can plug the 20 back into that one, the revenue function, and get that y equals 220, right? Because 11 times 20. Right, so my production level to break even is 20. The dollar amount that my revenue and cost will both be when I'm breaking even is 220. So 220 coming in, 220 going out, I've broken even. So if I want to start to turn a profit, right? I don't know why I'm zooming out. So need x equals 21 to turn a profit. Okay. And when you're doing the online homework, just pay attention to the wording in the problem. And the one that I have in mind, the one where, like, even if you get a whole number, you have to round up to the next whole number. That one, like, in the problem, it tells you that. Right below the entry box, there's like some hint saying, hey, remember, I forget the wording, right? But it's something like, hey, remember, you need to be profiting. If you find a whole number, you still need to round up to the next whole number. It's in the problem, like below the entry box. Anyway, that's how that one goes. Just whenever you are looking for a break-even point and your functions are linear, and or if you're thinking about supply and demand curves, you're looking for the equilibrium quantity with in microeconomics. Anytime you are looking for two things that are linear functions to be equal, well, you're looking for an intersection of two straight lines, two linear graphs. I mean, that's like this break-even point. This is a consistent, independent system. Like, that's what that graph represents. So anytime you have two linear functions, you want to find out when they're equal, you're essentially solving a pair of linear equations. Like, it's kind of the same thing. And the same approach can be used. Okay, what's next? Guitar Factory has a production cost, or cost of production, C of X equals 75X plus 50,000. If the company needs to break even after 150 units sold, at what price should they sell each guitar? Round up to the nearest dollar and write the revenue function. Okay, so the revenue function in general, and we can follow like this one right here, right? This says a revenue equals 11x. X is the number of. Okay, it didn't say what X is. X is burgers sold or something. I don't know. X is customers, something like that. So the revenue is $11 per person served. Like maybe it's an average or something, right? So the price of the product times the number that you're selling, that's the revenue. And we can kind of follow that model. So this revenue function down here, revenue is going to equal some price times X the number of guitars sold. Or in other words, we can call this a function R of X equals P for price times X. And X is the variable, P is a numeric price. And they're asking us, at what price should they sell each guitar? They're asking us to find that P value. They want to know this number P. What is that supposed to be? Now, we're breaking even after selling 150 guitars. Okay, so that means that C of 150 needs to equal R of 150. If you're breaking even at 150, well, then your cost at 150 and your revenue at 150 should be the same, right? So I can plug 150 into this cost function. So 75, not sure how I got 27, 75 times 150 plus 50,000 equals, well, R is P times X. This is P times 150. We don't know what P is. It's the price. We're going to have to figure that out. So hopefully you've noticed, maybe you've noticed, this is a linear equation with one variable. We can solve that, right? Total up left-hand side, divide both sides by 150, and that's what we'll get. So on the left-hand side, when we do 75 minus 150, I think I know what that is. Well, no, I don't. I was thinking about something else for a second, so let's get a calculator out. I'm tempted to try to ballpark in my head, see how close I can get, but let's skip that. So I get 11,250 for that product, and plus 50,000 is 61,250. Okay, and we'll divide 150 on both sides. So I get 75. I feel like I've made a mistake. That seems too nice and easy. I'm gonna do that one more time. Just, the fact that came out so nice and neat seemed a little weird. So 75 times 150, right? That's 11,250 plus 50,000, 61,250, and then divide by 150. Ah, yeah, it's not 75. I typed something in wrong. Okay. Okay, so it's 408.3 repeating, and I'll round to two places. Let's imagine that's like this is a dollar amount, so two places would be the nearest cent. So that tells me that the price should be $408.33. That's the price per guitar they should charge, so that they'll break even when they sell 150. Okay, so maybe you can see how this is. Problems or examples 7 and 8 are kind of the same question, sort of, but they're asking about the same basic kind of thing. But one is asking you to, here's two functions, find out when they cross. And the other one is, hey, here's a function and some other partially formed function, and they need to cross at the specific x coordinate, complete what the second function looks like. What's the price? But it's kind of similar in that the same pieces are there. Anyway, so that's the first part of Module 4 is just systems of linear equations. Maybe that wasn't, maybe, I think that these types of problems can feel very tedious because there's a lot of, it can feel like guesswork. There's a lot of steps. how do I want to put it? There are a lot of choices. You can do substitution, you can do elimination. You could pick this equation or the other equation. Pick x to start with, pick y to start with. You get to choose however you want to do it. So there's maybe in a given example, there's 10, 15 different ways to do it because there's a choice at every step, and you end up doing all the same things overall, but the order in which you do them is up to you, and some approaches might be slightly easier or faster than others. And so it can feel very tedious because it can feel like you're guessing and checking and guessing and checking, but you kind of are doing that. And just by doing enough of these, you kind of get used to the overall pattern, and it's not super difficult. But it just takes practice to get to that point. Anyway, next thing is linear inequalities in systems. So this is not much. Basically, we're layering on top of what we just talked about, including, now we're going to talk about inequalities rather than just equations. And it gets a little bit more complicated, and you'll see what I mean. But then it also enables a really neat technique called linear programming. That's module 5. So that's why we're doing this now, so that in module 5 we can use it to solve some problems. So determine whether each given ordered pair is a solution to the system of inequalities. Okay, so this is very much like what we already did with the pairs of equations. In order to see if a ordered pair solves a system of inequalities, you just plug it in to each of the inequalities and check that it solves it, right? Kind of like up here, when we were plugging in to check that this ordered pair solved the pair of equations. Kind of similar. We're going to do that down here. But let's talk about solutions to inequalities that are not in two variables first. And this is something you're probably already familiar with. I believe this was part of module 1. Yeah, it was part of module 1. So if you have something like 3x plus 1 is less than 10, okay? You can solve that inequality, right? That's just module 1, so we should all be able to do that. You could also just guess at numbers. Like if I say, what about x equals 0? Is this a solution, right? Well, if you plug in 0 to the left side, to the x on the left side of the inequality, you'll have 3 times 0, which is 0, plus 1 is 1. 1 is less than 10. So yeah, that is a solution, right? It's not the only one, right? Because x equals 1, that's also a solution, right? You plug in 1, 3 times 1 is 1, plus 1 is 4. 4 is less than 10. So yeah, that's a solution. Of course, like I was alluding to, we all kind of know that you can take this equation, or I shouldn't say equation, inequality, subtract 1 on both sides. So 3x is less than 9, then divide by 3, x is less than 3. So now we know, well, any number that's less than 3 will be a solution to the original inequality because we used algebra to isolate x, right? Well, over here, you can't really do that. We'll look at how you find solutions to a pair of inequalities, but it's not purely algebraic. There's a graphical approach. You have to draw it out. But we can start with looking to check, is this a solution or not? So I don't have a whole lot of room here. So I guess what I'll do is I'll just zoom in and hopefully everything will fit. So we're going to plug in this ordered pair into the top equation. So 3 times 3 plus negative 3, right? So 3 times 3 is 9, minus 3 is 6, minus 3 is 6, which is greater than 5. So that order pair solves the first inequality, okay? Now it's an inequality, so we're not trying to get the left side to be 5. We're trying to get the left side to be anything greater than 5. We don't really care what it is, as long as it's greater than 5, then it checks out. Then I plug into the other one, so 2 times 3 minus negative 3. So 2 times 3 is 6. Negative 3, that's plus 3, that's 9. And that is less than or equal to 10. So that checks out. So yes, this is a solution. Okay. And the other one, I'm kind of expecting it not to be, but I could be wrong. So plugging in 7, so 3 times 7 plus 1. Well, that's what, 22, right? 21 plus 1, which is 22, which is greater than 5. Okay, so that checks out. Plug into the other one, 2 times 7 minus 1. So that's 14 minus 1, which is 13, which is not less than or equal to 10. That's greater than 10. doesn't work. So this is not a solution. Okay. And then the other one is basically the same thing. So plugging in 2 comma 3, so 7 times 2. Actually, I'm going to zoom in a bit for now. So 7 times 2 plus 2 times 3. So 14 plus 6 is 20, which is greater than 14. That checks out. 5 times 2 minus 3. So 10 minus 3 is 7, which is less than or equal to 8. So that checks out. Great. And the next one, I'm kind of expecting neither, it not to match with either. That's just my expectation. So 7 times 7 plus 2 times negative 1. So 47, right? Which is greater than 14. Oh, okay, so that matches that one. Oh, I didn't write is a solution. Hold on. And then plugging into the 7 comma negative 1 to the other inequality. So 5 times 7 minus negative 1. So that's what, 36? So that does not match that last one. This is greater than 8. It's not a solution. Okay. That's how those go. The homework probably has like only a couple of these. This is not something. Well, okay. So because we're going to be doing linear programming, this checking is something we will do again later. The process of linear programming requires you to set up some graphs, which we'll be doing in a moment. And then you have to then go do some checking on some intersection points. So you'll see that next week. So this is not merely as a stepping stone into what we're about to do, although it is that. Also, we need to do this again later. So don't discount this as being unimportant. Make sure that you understand this and that you can see that you only have to not match one of the inequalities. The proposed solution only needs to not match one of the inequalities to be disqualified. Okay, so I want that to be very clear. Okay, what's next? Graph the feasible region for the system of inequalities. Okay, feasible region, what does that mean? Well, the feasible region is another term for like the solution region. What is the region where the ordered pairs, which are solutions, where does that live? Where is that? So basically, the way I think about this, and there's lots of ways to do it, and the textbook might do it slightly differently. So how you do it, like on an exam, is up to you to some degree, in the sense that if my approach differs from the textbook, well, if the textbook makes more sense to you, all right, then you should do it that way. You shouldn't try to do it my way, despite it being harder for you. Whichever method you find that works is fine, right? Obviously, it has to get the right answer, and you have to show your work. But I just want to point out that the way I do this might be different from the way the book shows to do it. So here's how I do it. I like to think about this is the original problem, and we're going to convert it into the boundaries for these inequalities. Okay, so basically, what do I mean by that? I think it'd be best if I just show you and then point out, like sort of post hoc, hey, this is what I meant when I said these are the boundaries. So I'm going to rewrite this, and I'm going to change the inequalities into equal signs. So 2x plus 4y equals 8. And then on bottom, y equals 3/4 x. Okay. And then I'm going to basically graph the two boundary lines on the grid here. And it's a little blurry because I'm zoomed in. Like normally it would look a little bit better. Let's say that the grid units go by ones. Okay. Each grid line is 1 unit. So there's a couple ways to do this. I noticed that first of all, I really could just divide both sides of this equation by 2. That would simplify things. And then I can take this equation, and if I want, I can multiply by 4 on both sides. I don't have to do that because I want to graph these, but I might want to, as part of graphing them, I might want to find their intersection point to make sure that my graph is really accurate, right? So that's what I'll do first. I'm going to take this top equation, and multiply by 1/2 on both sides, or in other words, divide by 2 on both sides. Okay, and then the bottom equation I'll multiply by multiply by 4 on both sides. Okay, so top equation divided by 2 on both sides. We get x plus 2y equals 4. Okay, and on bottom equation, multiplying both sides by 4. So 4y equals 3x. Okay. So then what I'm going to do is I'm going to, oh, you know what? I just realized we had a 4 here and I turned it into a 2. So you know what? Yeah, this is going to happen sometimes. So this is good. You see what happens when you make a misstep and you realize it? Well, just go back and fix it. It's fine. You're going to have that happen sometimes where the thing that you think to try first actually is not the best thing to try. So we're going to do that. And then I can subtract the two equations. Now, I don't have to get 3x onto the other side first if I don't want to. I mean, I can, but I'm going to subtract the two equations. My stylus stopped working again. Oh, there it goes. Okay. So, yeah, I'm going to subtract the two equations. So I'm going to have 2x plus 0, right? The 4y minus the 4y makes 0, equals 8 minus 3x. Okay. So I'm going to add 3x to both sides. So 5x equals 8, and then divide by 5 on both sides. So x equals 8 over 5, or in other words, 1.6. Okay. So then the y coordinate, I can take that and plug that number back into there and get y equals 3/4 times 8/5. So the 8 and the 4 reduce. So we get 6/5. Or if you want, 1.2. Okay. So there is the ordered pair where they cross. You don't always need to find that, but it can be helpful sometimes. Okay. So now the other thing I notice is this. I want to graph these. So the intersection point is great and all. It's not the only way to do it. I just was thinking that would help with that one. Another thing we can do is, I'm kind of all over the place on this one because there's multiple ways we can do things. You don't necessarily need the intersection point, but it can be helpful. So I'm going to backtrack a little bit. I'm just going to graph this equation. The y-intercept is 0. The slope is 3/4, right? The rise over 1 is 3 over 4. So I'm going to graph that one in blue. So the one of the points is the origin, okay? And then the slope is 3 over 4, so that's like right there. So the line will be something like this. Now later, the ordered pair 1.6, 1.2, which is right about there, right? That's going to be the intersection point. Okay, so just keep that in mind. Now I want to graph the other line. I'm going to take this one. I'm going to copy it down here. And I'm going to divide by 2 on both sides when I do that. So x plus 2y equals 8. And then I'm going to isolate y because I kind of like this into the slope intercept form because that might make it easier to graph. You don't have to do it that way. We could use intercepts. Yeah, let's use intercepts. Let's do that. That'll be fine. So if I want to graph this with intercepts, we can make a t-table. I say, well, if x is 0, what would the y value be? And if y is 0, what would the x value be? Right? That's x and y intercepts. So if I put in x for 0, well, then I'll have 0 plus 2y equals 8. So y equals 4. Okay. And if I put in 0 for y, you'll have x plus 0 equals 8. So x equals 8. So that was kind of straightforward, although we could have used the slope-intercept form. That would have been fine too. So the intercepts are 0, 4, and 8, 0. So 0, 4, so right about there. Okay, and then 8, 0. Just right about there. So right about there. And the oh, hold on. No, that's not quite right. Hold on. Because remember I said that the order pair 1.6, 1.2, that would be the intersection point, and then that's not what we found. So I've got a mistake somewhere. Okay, that's fine. We'll find it. Okay, so the first thing I'm doing is I'm thinking about this one here being graphed, and the slope is 3/4. Rise over 1 is 3/4. That seems fine to me. I'm starting to think there must be a mistake over here, because what we did here was so straightforward. How could we have a mistake? But y equals 3/4 x. That seems to be right. Also, you might have noticed this grid is not totally squared up. Like the little grid, the little squares aren't perfect squares. I don't think they're off by that much though. So rise over 1 was 3/4. Okay. Oh, I see the mistake. Yeah. Okay. Probably some of you are shouting at your screens. Okay. Yeah, it was a bit too cavalier. When I divided this equation by 2, right? That makes 1x, 2y equals 4. So I had the wrong number there. Okay. So this is a 4, which means this is a 4 and this is a 2. This is a 4 and this is a 4. So this is a 2 and this is a 4. Sorry about that. So let me pause there so you can, maybe I did that quickly. So we'll pause a little bit so you can catch up if needed. Okay. So that means we need to erase some stuff. Okay, so the intercepts were at 4, 0 and 0, 2. There. And there we go. Now this lines up the way it was supposed to. Okay, cool. So sorry about that, little mistake. So we've got the two boundaries graphed. Okay, now here's the next part. It's very important. We need to shade the right side of each graph because the solutions to this inequality, these are all going to be either this side, okay, those are all solutions, or this side, those are all the solutions, okay. Now, there's a couple ways to do that. I find that the best way is to leverage what we talked about, right here, where we pick a test point and then we just plug in and see, is this a solution? Okay, so again, either all the solutions are here, and we just pick one of those points at random, pick any one of them, plug into the inequality to see if that's a solution or not. And if it's not, well, that means, oh, well, then it has to be all the ones on the other side. Okay, so with one test, we decide which side it's on. I find that the origin 0, 0 is often a good one to pick because it's easy to total up. So if I say, oh, is 0, 0 a solution to that inequality? Well, 2 times 0, zoom in a bit, 2 times 0 plus 4 times 0. Well, this equals 0, which is less than 8. So no, it's not a solution. So that means that the solutions to that first inequality are above the line. Also on the line, including on the line. It's like the x-intercepts, like 4, 0. 4, 0 is a solution to that inequality. And the reason for that is that you have a greater than or equal to. So if you put in 4, 4 for x and 0 for y, then it is a solution to the inequality, right? If you put in 0 for x and 2 for y, it is a solution. Those ordered pairs are solutions. Okay. Now we're not done, because also we need to know, well, are the solutions to the other one, where are they? The solutions to this one, are they on this side or are they on this side of that line? So you have to keep track of which line, like when you're drawing it, you have to keep track, okay, this inequality is this line in the graph. And you have to keep track of which one is which. You can't, if you lose track of that, obviously you're gonna have a hard time. So now we just pick a point. It doesn't matter which point we pick. Okay, so I'm gonna pick something like up here, like say 1, 8. 1, 8. In fact, let's do this. I believe that counted right. 1, 2, 3, 4, 5, 6, 7, 8. 1, 8. So if I plug 1, 8 into this inequality, whether it solves the inequality or not will tell me which side of that line the solutions are on. So, yeah, 1, 8. Checking the other one. So 8 less than or equal to 3/4 times 1? Question mark? Well, no. 8 is not less than 3/4 times 1 because 3/4 times 1 would be 3/4, right? So no, it's not. So the solutions are on the other side. Oh, so I'm trying to make this somewhat neat. So when you're doing the homework and you're turning in your written work, if you have like a tablet, like an iPad or whatever, you could just do this. The feasible region is the region that overlaps. Okay, that's the feasible region. If you don't have like a tablet or an iPad where you can, or also if you're doing it on paper, like if you have like color pencils or something, or if you have some way to color it that it's very clear, that's fine. If you don't, in the other one, when we do that one, I'm going to show you a different way to indicate where the solution set is. There's a couple of different ways to do it, but this is just one way. So there is the feasible region, okay, and I've labeled it. Another thing we could do if we wanted to is instead of coloring coloring the proper side of each of the boundaries, instead I could work out what they are and then only shade in the feasible region itself, the coverage of both of those solution sets, both sides where we have the solutions to each inequality. I can then shade in just the proper one. That if I want to, I can. I don't have to do that. Maybe that's better. I kind of prefer, since I can and I have the colors available, I prefer doing this. I think it's more informative about what's happening with the inequalities. So we're going to do this next one, and I'm going to not use the coloring in approach, because if you're doing this on paper with just pencil, you're not going to be able to do that, or at least it'd be hard to make it nice and readable. Okay. So with this one, I'm not going to bother finding the intersection point first. It turned out we didn't really need it, but I did lead me to catching a mistake. I'm not going to bother with that this time. I'm just going to find the intercepts of each of them and then graph the lines and go from there. Okay, so first thing I'm going to do is we're going to turn this into the boundaries. So I'm just going to make these equations. 2x plus 2y equals -4, -x plus 3y equals 9. And we'll have to come revisit these in a minute, okay? For a couple of reasons. For one thing, to decide, where is the solution, of course, but there is something else actually. Okay, so what I'm going to do is I'm going to just work out, okay, what are the intercepts of these? Okay, so plug in 0 for that first one. So 0 plus 2y equals -2. Oh, sorry, -4. And then divide by 2, y equals -2. So that's one of the intercepts. And if we put in x 0 for y instead, then we'll get x equals -2. So that's sorry, that's not an ordered pair. So one of the x-intercepts, sorry, the x-intercept is 2, 0, and the y-intercept is 0, 2. So I'm trying to brush through this. I probably shouldn't be. So that's the first one. So I guess I can go ahead and graph that. Yeah, let's go ahead and do that. So we'll do that one in gray. So 0, -2, and -2, 0. And again, we'll do this in gray. So it's going to be like something like that. So we line up just a little bit better. Yeah, that's fine. Okay, so there's one. Now, we did this with the first one, okay? The first inequality, which is a strict inequality. This is strictly greater than. What that means is, in the graph, this boundary should not be filled in, okay? Over in this other one, both of these were of the or equal to type, greater than or equal to, or less than or equal to, right? So there's solid lines because the points that are on the lines themselves, the boundary lines, those all will satisfy their respective inequality because the inequalities are or equal to. Now this one is strictly greater than. So the points that are on the line are not solutions to the inequality. So the way to indicate that is that we're going to turn this into a dashed line. And if you're using pen and pencil, you just kind of draw a dashed line. You can use a ruler to make a dashed line, or you can basically hopefully you know how to make you put down a ruler and you draw a dashed line, right? By picking up the pencil several times, right? Another way, if you're using pencil, is just draw the line and then go back and erase like pieces of it to make it a dashed line. That's the way I prefer to do it. Anyway, I have this tool that I can use here, so I'll just do that. So then the next one, so we'll find the intercepts of that one. I guess I'll do this in yeah, I'll do more of this in blue because that'll, in fact, let's do this. Let's make the colors all match. Okay. So the next one, intercepts of this one here. So we'll put in 0 for x, so negative 0 plus 3 y equals 9. So y equals 3. 0 comma 3 is the y-intercept. And then we'll put in 0 for y, so negative x plus 3 times 0 equals 9. So negative x equals 9, or in other words, x equals negative 9. So the ordered pair is negative 9 comma 0. Okay, and this one we'll do in blue. Okay, so 0, 3, and negative 9, 0. So something like that. That's pretty close. Okay, cool. And this one is an or equal to, so it's a solid line. Okay. So now we need to figure out where's my feasible region. And again, I'm not going to use the shading in like with the sort of marker tool. I'll use the pencil tool or the pen tool. It actually is a separate pencil tool as well. Anyway, so I need to pick test points. Okay. Let's do this part in red. And I think generally the origin is a good test point. So I'm going to pick this test point, and if this ordered pair solves both inequalities, that would mean that my feasible region is this region right here. If it does. If it doesn't, well, if it fails to solve either one of them, well, then one of the other regions, I actually want to leave that there, then one of the other regions will be the feasible region. So we'll just try plugging in 0 to both of these. So if we put in 2, 0 plus 2, 0, well, that is greater than negative 4. Yep, it sure is. Yeah, that works out. Okay, cool. So this red dot, this is on the proper side of the dashed line. Okay, now I'll try the other one. So negative 0, and probably you can already see where this is going, plus 3 times 0 greater than or equal to 9. Nope, that is not true. So this red dot is on the wrong side of the blue line. So that tells me is that the red, the dashed line, its solutions are on this side, but then the blue line, its solutions are on this other side. Okay, so the place where you see that overlap, that's where the solutions are. So if I want to do this a little bit more carefully, let's even do like this. So these solutions are there. Okay. And then the other solutions are, I'm making sure that when I do the second set of slashies, that they go the opposite direction. So it's very clear where the overlap is. Like you're not going to mistake where the overlap is. So that means that the solution set is like if I were doing highlighting, I would be highlighting this region here, right? Now we're not because I want to illustrate it, but that's where it would be. So that is another way to do that. So if you want to do it more like this, that's absolutely fine. If you want to do it more like this, that's absolutely fine. And then also, I didn't label it. It's kind of hard. It's kind of like, oh, we could try that. Feasible. Like that's not really readable, right? Yeah. But so we'll just say a feasible region like this. Like that, right? It's that one. Okay. Okay. What's next? Okay. Okay. So we have two application problems. All right. So use systems of inequalities to answer the following. Caitlin sells her drawing at the county fair. She wants to sell at least 60 drawings and has portraits and landscapes. Okay. Sells her drawings at the fair. Okay. She sells the portraits for $15 and landscapes for $10. She needs to sell at least $800 worth of drawings in order to earn a profit. Will she make a profit if she sells 20 portraits and 35 landscapes? Will she make a profit if she sells 50 portraits and 20 landscapes? Okay. So you probably don't need to graph for this one because it's proposing things, right? Oh, if she sells this and this, will she turn a profit? This is very much like this. There are proposed solutions. If there are proposed solutions, you don't really need to draw anything. So let's try to do this without drawing. I think the next one, though, might require drawing. We'll see how it goes. But we have to at least set up inequalities. So so she wants to sell at least 60 drawings. Okay, so this at least 60, this is an inequality, right? At least. That means greater than, right? Or greater than or equal to, right? If I say, oh, bring me some strawberries, and you're like, how many strawberries do you want, right? And I go, oh, I want at least 10. Well, you could bring me 10 or 11 or 12, right? It's a greater than or equal to. Portraits and landscapes. So there's two types. Portraits and landscapes. Okay. Now, what I'm going to do is I'm going to say, oh, well, portraits, we're going to call X the number of portraits, and landscapes, we're going to call Y the number of landscapes. Okay. So when you're doing these, you have to decide what X and Y is going to be. In general, you don't have to use X and Y. You could use P and L for portraits and landscapes. But in the online homework, it's gonna use X and Y for everything. And if you try to use other letters, it won't take it. So probably we should be doing it this way. So she sells portraits for $15. Okay, so this is a dollar amount for the portraits. So like number of portraits, which is X times 15, that'll give you the revenue from selling the portraits, right? And then landscapes for $10. Okay, well, 10 times Y, the number of landscapes, that's going to give you the revenue for landscape drawings that she's selling. Okay. She needs to sell at least, there's another at least $800 worth to turn a profit. Okay. So this part here, the at least 60 drawings, she just wants to sell at least 60. So like 30 of one, 30 of the other, 40 of one, 30 of the other to sell 70, right? Just the sum of the two quantities needs to be at least 60. So that at least 60 is telling me that, I'm going to change colors here, X plus Y is greater than or equal to 60. Okay. So I'm inferring an inequality from the description. And it might seem like this is not like a big inference. Like some of you were probably thinking it's kind of obvious. But, when you have this big paragraph, trying to write neatly here. When you have a big paragraph, oh boy, I'm not editing this out, by the way. There we go. Anyway, when you have a big paragraph, sometimes it's not going to be obvious. And maybe this one does seem obvious, especially when I'm highlighting like this. Obviously, that helps. But the homework problems are all going to be like this, where there's a description, and you have to figure out. You have to infer an inequality, and that's not always easy. And so some of the homework problems might be a little bit harder than this one. So then the dollar amounts, right? I'm told how much she sells the portraits for, how much she sells the landscapes for, and she needs to sell at least, that's another greater than or equal to, right? So 15x is the dollar amount for the portraits, and then plus 10y. That's the dollar amount for all of the landscapes she sells, right? If she sells 8 landscapes, that's $80, right? This needs to be at least $800. Okay? I'm not writing a dollar sign, but it's dollars. So, will she make a profit if she sells 20 portraits and 35 landscapes? Well, that's only 55. That's only 55 drawings. So, that's not what she wants, but the question is, will she make a profit? Okay, well, if we put 20 and 35 into this inequality, do we get at least 800 is what that's saying. Okay? So, for this question, if she sells, we're going to plug 20 and 35 into that second inequality. So 15 times 20, because that's 20 portraits, plus 10 times 35 landscapes. So that's going to be, well, 15 times 20 is 300, plus 350, which is 650, which is less than 800. The answer is no. She will not turn a profit if she sells that many. It's also not, she wanted to sell at least 60. So doing 20 of one and 35 of the other doesn't match either of these inequalities, right? Now, second question. So will she make a profit if she sells, let's go green on this, if she sells 50 portraits and 20 landscapes. I'll do that over here in green. Okay, so 15 times 50, that's a lot of portraits, plus 10 times 20. And notice also that this is 70 drawings total, which is what she wanted. So 15 times 50 is 750, plus 200, so 950, which is greater than or equal to 800. So yes, he does make a profit. And we didn't really have to draw anything because the question was proposing solutions to the system of inequalities. So all I had to do is figure out what's that system of inequalities. I have, oh, and by the way, I did say this, but maybe I should put a finer point on it. This is just like count. I have an inequality that relates how many there are, right? There's x of this one, there's y of that one. The total needs to be at least 60, right? And then there's another one which is the revenue. Okay, it's the dollar amount. And so whenever you are setting up your inequalities, numbers of the same type, like dollars and dollars, probably going to go, oh, sorry, dollars, dollars, and dollars again, right? Dollars showed up 3 times, and those $3 amounts, they're part of my revenue inequality. So when I'm reading one of these problems, I'm looking for which numbers are they giving me that are of the same type of thing, because those are probably going to go together in an inequality rather than being separate. Like the 60 drawings and the $800 are in separate inequalities. Anyway, so we answered the 2 questions. We didn't have to draw anything. Maybe this one will require drawing. So Juan is studying for his final exams in chemistry and algebra. He knows he only has 24 hours to study, and it will take him at least 3 times as long to study for his algebra. At least, I'm reading, at least 3 times as long. I'm just going to highlight at least for now. The 3 times as long is going to be important. But yeah, so at least 3 times as long to study for his algebra than his chemistry. Can he spend 4 hours on his chemistry and 20 hours on algebra? Can he spend 6 hours on chemistry and 18 hours on algebra? I think we're not going to need to draw anything. We just don't need to do that. So if he only has 24 hours, that's a limitation. That doesn't say less than or greater than anything like that, but only has is a limitation. So his total hours is less than 24, right? Or equal to. Total hours is less than or equal to 24, right? But then we're talking about, he's studying for chemistry and algebra, and we're talking about how long it takes for the studying, and then we're asked, well, what about 18 hours on this and 6 hours on this? So the 2 variables, x and y, these are numbers of hours. And I'm going to say that if we say that x is hours spent on chemistry and y is hours spent on algebra, that means that we can put these 2 things together and say, oh, we have an inequality. X plus y is less than or equal to 24 hours. Okay. And then the other part of the inequality, the 3 times as long part, it will take him at least, which means greater than or equal to, right? 3 times as long to study for his algebra than his chemistry. Well, that's a grammatical error. It should be as his chemistry, but whatever. This is a little bit misleading. Let's highlight this. Yeah, okay. This whole thing really should be highlighted. At least 3 times as long to study for his algebra as his chemistry. And you might think, oh, okay, that means something's going to get multiplied by 3, which is true. Now, x is the number of chemistry hours, y is the number of algebra hours. It's going to take him 3 times as long to study for algebra. So algebra is the greater amount, right? Algebra is more. So you might think, oh, that means 3y, 3, oh, wrong tool there. That means, okay, 3y. I'm pretty sure I pressed the button. It's not working. Sorry about that. Struggling with the interface here. So you might think, oh, 3y, at least, then his chemistry. That's, oh, I'm sorry, x. No, I got it right. Algebra is y, x, right? Well, this is incorrect because what this says is that let's put it this way. If I plug in a number for y and a number for x, if I plug in, say, 10 for y, right? Oops. If I plug in 10 for y, that means that x could be as much as 30, right? If y is 10, it's not because we only have 24 hours. Let's ignore that for a second. If y is 10, well, then 3 times 10 is 30, so x could be as much as 30. But then x is more, right? But it's going to take him at least 3 times as long to study for algebra. Algebra has to be more. So this 3 belongs on the other side, okay? Y is greater than or equal to 3x. Because then whenever you pick a number of hours for chemistry, say it's 2, if x is 2, that means that algebra has to be at least 6, which is the greater number. So it's a little counterintuitive that the variable of the greater amount doesn't get the multiplier. But one way to think about that is, well, the variable with the greater amount doesn't get the multiplier because it's already the greater amount. The x needs the multiplier in order to try to match up with the y, right? Hopefully that kind of makes sense. I know it's counterintuitive, but hopefully that made sense. I'm going to erase most of this because we don't need any of this now. Well, not any, but we don't need most of this now. So here we go. Here are our inequalities. Okay. Now, I don't necessarily need to draw anything because it's just proposing solutions, but I don't want to do it the same way as this one. I want to illustrate what you would do because the homework problems are going to require it in some cases. Like you might be asked to figure out an ordered pair that works. So I'm going to go ahead and graph these. Now 24 is kind of a big number. So I can't, if I just say that this grid goes out by 1 unit each time, then it only goes out to 10. That's not going to work. So I'm going to say that each unit is 3 units, or each grid line is 3 units, okay? So like this is 30 right here, and this is 30. And this is 30 right here. Okay? So this one, when you have x plus y is less than or equal to 24, I mean, the intercepts are pretty easy because if you plug in 0 for x, well, then y would be up to 24, right? If you plug in 0 for y, x would be up to 24. So 24 is the coordinate of both of those intercepts. So that'll be like from here to here. Okay. And I'm only going to draw in the first quadrant because if we go out here, this is like having negative hours for chemistry, I guess, or whichever one. Algebra, that's negative hours for algebra. You can't have negative hours, so I'm only graphing quadrant 1. Really, this grid probably should have been a little bit different and have the axes in the bottom left corner, have the origin in the bottom left corner, but whatever, that's fine. Okay, so there's one graph, and if you pick a test point, if you do a test point of the origin, And you go, oh, does the origin solve this? If you plug in 0, 0, well, then yeah, 0, 0 is less than or equal to 24, right? So the feasible region so far includes all of this space here so far. Also, by the way, I kind of alluded to this, but of course, x is greater than or equal to 0. Change the size there. X is greater than or equal to 0, and y is greater than or equal to 0, because you can't have negative numbers of hours, right? Okay. So now when I want to go graph this one, okay, well, I can just use the y-intercept and the slope to graph the boundary. So the y-intercept is the origin, the slope is 3. So I can just do this. Go start at the origin, and then use a slope of 3. So like that. Okay. And we need y to be greater than or equal to that. So if we take, say, the origin won't work because the origin is on the line. So that won't tell us anything. But if I go say, oh, well, what about 3, 3? Well, actually, this is 9, 9, right? Because of the scale. These go by threes. So if I plug in 9, 9, well, 9, 9 does solve this one, right? 9 plus 9 is 18, which is less than 24, so that works. Does 9, 9 solve this one? Well, it turns out not to, right? If you plug in 9, 9, you'll have 9 is greater than or equal to 3 times 9, which is wrong, right? That's incorrect. So this is not the solution, okay? Solutions are actually over here, okay? And actually, I do want to highlight this with the fill-in color, not the lines. You'll see why in a second. Oops. Yep, not perfect, but close enough. So that's the feasible region, right? And then we can go on to the questions part. So can he spend 4 hours in chemistry and 20 hours on algebra? 4 in chemistry and 20 on algebra. So that's x equals 4 and y equals 20. Okay, x equals 4, algebra is y. Yeah, 420. So that's going to be like, well, 4 is like right here. And 20, well, that's going to be 3, 6, 9, 12, 15, 18, 21. 21 is here. So that's like right, boy, it's right on the line. It's like right here. It's hard to say. Does it, which side of that one does it fall on? And I've done this by hand, so I'm not totally sure. I think what we need to do is plug that in and go, oh yeah, 4 and 20 would be less than or equal to 24. So that would be using up the entire 24-hour time period. So that actually, it should be like right on here. Oops, sorry, struggling with the interface. Okay, I guess I will be cutting part of this out. The screen share stopped, and I don't know why. Or no, oh, the app crashed. This app crashed. Okay. Yeah, I think I'm not going to take the time to edit that out. How much do we lose? Oh, we didn't really lose very much. Okay. Yeah, when the app crashes, you lose some of the, what you had just done in the file. So like I said, I think I'm not going to bother editing that out. It just resolved quickly, so let's just keep moving. So like I said, we were looking at the ordered pair 4 and 20, right? 4 for chemistry and 20 for algebra, and that turns out that it is right here, like right on that line there, right? So that does work. It's on the edge there, okay? And then can he spend 6 hours in chemistry and 18 hours on algebra? So that would be 6, 18, okay? 18 hours on algebra. Okay, well 6, yeah, so 6 is like right here, right? And 18, right here. Yeah, that would be like right on the edge here. So yeah, either one of those would work. They're both edge cases. They're right on the edge of the feasible region, but yeah, they both work. So the answer to both is yes. Okay. that's basically it. Sorry about the hiccups here and there. That's it for module 4, I guess. We're almost at 2 hours, so that's kind of why I was trying to rush at some point, or at certain points. So yeah, that's basically it. Like I said, so we're going to expand upon this in module 5 to include what's called linear programming, where we take some of these basic steps of answering questions about inequalities and does this ordered pair sit in the feasible region, stuff like that, and we'll expand that to solving more complicated problems. Anyway, that's it for this week, and I look forward to making the next one.